Hello students, it's Mr. Gopal back with another video about some fundamentals. Today we're going to talk about Newton's three laws and how to use them. So the title of this lesson is Connecting Newton's First and Second Laws. And the focus question is, how can we solve problems involving Newton's first and second laws? So they have a simulation for you to take a look at here, but also they have some simple setups for you to practice using the first and second laws at the beginning. And the overall objective is to use our fundamental equation, force equals mass times acceleration, and to identify ways to change the acceleration of an object. And so for this, I've made a little background document for you that I'm going to walk you through and that you should keep close as you're going through all of the mechanics and kinematics and even dynamics aspects of Regents physics. So here's our document. It's our notes for day 6, but you could even make a copy and relabel it however you want. First things first, we have Newton's three laws of motion, and they are named for Sir Isaac Newton, the father of classical mechanics. So when I'm talking about mechanics, I'm talking about laws of forces that govern the behavior of different objects, all right, in an environment. Specifically, when I talk about behavior, I'm talking about movement and rest. So when I say that Newton's the father, that means that all of this goes back to him. He came up with the entire field of this foundational information that you're learning right now. And I want to talk about these three laws. So I've got the language. I touched it up a little bit just to make it a little bit easier to comprehend. The original language can be a little formal and abstract and distant, and therefore hard to parse. So the first law says that an object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by a net external force, all right? And so here's my explanation. Obviously, we're starting from ground zero, and that is just making observations with our eyes about the objects in our environment, all right? And those observations are grounded in the term inertia. Inertia is a governing principle for all the bodies that we look at. And what it means is resistance to change. Therefore, in another sense, what it means is that if an object is already moving, it's going to resist stopping moving. And if an object is resting, it's going to resist being put into motion, all right? It requires a force either to be put to rest or to be put into a state of motion. And so we have to calculate what we call the net force on an object to see if it will change its behavior. So if we exert a force on an object in one direction, it still will not change its behavior if there's another force in the opposite direction with the same magnitude. Magnitude is my fancy scientific term for size, okay? So I use magnitude to be very specific because if we talk purely in terms of numbers, we can dispense with the vector aspect of a quantity. So the vector aspect is crucial to think about when it comes to force. And so we want to break things down into both their magnitude or size and the direction that they're moving in. Classic example, I have my water bottle here. It's at rest on this coaster, okay? You can see that there. Got a little coaster here, and I'm going to put it on my table. Now, if you think about that object, all right, it is at rest, but there's a lot going on there, okay? So let's say that I have this box represent that water bottle, okay? And the coaster is right below it. It's resting on my table. Let's say that it's just resting simply on the table for simplicity's sake. So I'm going to put a red table right here below it, all right? We know that the force of gravity, which Newton is also responsible for conceiving of, is pulling it down towards the earth, all right? That is a pulling force, pulling it down, and I'm going to label that F sub G. Now you might think to yourself, well, wait a minute, if it's being pulled down, why is it not constantly going down? But there is an upward force from the table that is equal in magnitude, meaning size, and opposite in direction to my force of gravity. So I've got that one represented with this purple arrow. and I made them roughly the same size to represent that they are equal in magnitude. All right, and I'm going to label this one F sub n. All right, and that stands for normal force. Okay, so here's my normal force, and here is my force of gravity. And so the reason why this bottle is actually perfectly at rest is because I have force of gravity pulling it down with one magnitude, and I have the normal force going in the very opposite direction upwards with equal magnitude. So those magnitudes cancel out, and I can say that my net force, which I represent as F sub net, is equal to 0, okay? That's because if I applied vector quantities to my force of gravity, since it's pulling downward, we traditionally focus on downward meaning negative direction, all right, and upward being positive. So the negative and the positive, when they're equal numbers, let's say it was 5 newtons down and 5 newtons up, that would be -5 plus 5, and I would get a net force of 0. So the net force acting on this bottle while it is resting on a table is 0 because the normal force and the force of gravity cancel each other out, and therefore it's at rest. And now, if I wanted to say move it, I would have to apply a force to it. So I'm applying a force with my hand right now, and so the net force while it's moving around in the air on it is not 0, and that's why it's accelerating back and forth. All right. So there we have a simple illustration on the first law. All right. The second law, it helps us calculate forces. We know that force is equal to mass times acceleration. So we're going to multiply the mass of whatever our object is that the force is acting on by the size of its acceleration or the magnitude of its acceleration, and we will get the force from that specific source, you could say. So again, the force of gravity, that's from the Earth. The normal force, that's from the table, okay? So we can calculate the force of the table on the bottle as the normal force. We can calculate the force on the bottle from the Earth as the force of gravity. And in order to figure out its magnitude, we would have to figure out how much it's accelerating and multiply that by the mass of this bottle. Now, also, I make a point here that if we have the mass and we're able to calculate the magnitude of the force, we can go work backwards and find its acceleration. If we have the mass and how much it's accelerating, we can find the force. And finally, if we have the mass, if we have the acceleration and the force, then we can calculate the object's mass. Final law that I want to talk about is the third law. I know the third law isn't covered in this particular lesson, but I just want to illustrate this so you understand a little bit about why we see what we see, okay? The third law says that every action has an equal and opposite reaction, all right? And that means when we're talking about forces, the forces between two objects that interact somehow are equal. However, their masses are rarely equal, and therefore their accelerations may not be equal. So if I reach over and I push against this wall, all right, I have this fireplace connected to my wall, so I'm pushing against the whole wall when I do it. Obviously, it feels like it's pushing me back, you know, and my hand hurts a little bit from the size of the force that I'm exerting on it. You might think to yourself, if there's an equal and opposite reaction, why don't I see the wall moving? Well, the thing of it is, even though the forces are equal, the wall is so much more massive than me and the amount of force I'm putting in with my hand that I can't possibly get the wall to make any sort of movement. It is linked down into the foundation. It's probably many, many tons in terms of its weight, okay? And so they're highly unequal masses in this case, and so its acceleration is going to be negligible. We won't see its acceleration because it's so much more massive than me. Likewise, if I had a golf ball and a bowling ball and they rolled towards each other and then bounced off, the bowling ball is so much more massive than the golf ball. So what you might see is that they're exerting equal forces in opposite directions on each other, but the golf ball is going to accelerate away much more dramatically because of the bowling ball's much greater mass. All right, and the bowling ball, on the other hand, it may not be all that affected by the golf ball, since the golf ball has such a smaller mass than the bowling ball. So we see these kind of discrepancies in the relative mass of things all the time when they're interacting in terms of forces, and therefore we see unequal behavior in terms of acceleration between these objects. Now, I just want to bring all this information to bear on some problems, okay? So we have some simple problems here. I want to take a look at this last one just to give you a taste of what it's like to have two of the quantities and rearrange the equation. So if we know that there's a net force of 100 newtons exerted on a ball, and we know that ball has a mass of 0.72 kilograms, we can take 100 newtons and divide it by 0.72 to get our acceleration. That's because since F equals ma, I'll write that right above, since F equals ma, I can divide both sides by m, and I can say that F over m is equal to a. All right, then I can just plug in my information. And don't forget, when I say a Newton is equal to a kilogram times a meter, all per second squared. Or sorry, I can just write it like this, second squared. All right, we know that we measure acceleration in terms of meters per second squared. That's why we get an answer like that. We know that we measure mass in terms of kilograms, while we measure force as mass times acceleration. So newtons are technically kilogram meters per second squared. Finally, I want to talk about one of these complicated problems. So you have this really interesting simulation that I'm going to let you look through. Let's talk about this graph of force versus time. All right. So they say the graph shows the forces acting on the boat at 3 different times. All right. For the sake of simplicity, we're assuming the force is constant for a period of time, then suddenly changes to a new constant value rather than changing gradually, and the drag force is constant in this simulation. Okay. So I'm going to put in some values and explain what we might see in the simulation at that point. So we know force is graphed on the y-axis here. There's force over here going up and down. All right, remember it can be negative values depending on its direction. And then we have time on the x-axis. All right, so time is on the x-axis going this way. So time is moving forward from 0 to the right. Now, if I graph some values, let's talk about what could be happening. So for example, if for the first 2 seconds, I have a net force of 0 on the boat, that means one of 2 things actually. What we might assume is that the object is at rest, and that's one valid assumption. However, remember the first law, all right? We need an external, or we need a net force acting on the boat that is non-zero in order to see a change in its behavior. We can have a net force of 0 when the object is in motion, as long as it is not accelerating. Okay, and this is one of the most difficult things for students to understand. So picture the boat cruising at 5 meters per second. Okay, since it is not accelerating, it's not getting faster or slower than 5 meters per second, we can say that the net forces acting on the boat are equal. All right, and we can take a look in a later lesson about what that might look like in terms of a force diagram or a free body diagram. But either one of those things could be happening here. So I'm just going to label that on the screen in blue. So that means either object is at rest, or let's say the boat is at rest, or boat is traveling at constant velocity. Okay. Now, if we go to a later point, and let's say that we increase the force to, I'm going to use a new color. Let's say we increase it to 2 newtons. This would mean, since it's a positive 2, let's assume that that stands for right, since traditionally right and up are positive and down and left are negative in classical mechanics. Let's say that the boat is accelerating then towards the right. And for depending on how long this 2 Newton force is the net force acting on the boat will accelerate faster and the boat's velocity will increase to greater and greater magnitudes over that period of time. So if I extended this another second, by the end of it, it would be accelerating at a much faster rate. Now let's say one final leg of this journey, I reverse, undo that because I want to put it exactly on -2. I reverse and I have a net force of -2 on this boat. That would mean now that it is probably accelerating to the left. All right. So again, net forces that are non-zero mean the object is accelerating in either direction. Okay. And so let me just label that again. I'll use blue for both of these. So in these cases, we can safely say the boat is accelerating. Okay, and for the red, it's accelerating right. And for the blue, it's accelerating left. And again, the reason for that, well, the net force is not equal to 0. So I hope this video helped you capture the 3 laws of motion, a little bit about how we rearrange F equals ma, or the second law, to solve simple problems, and what it means to have a net force of 0 or non-zero. Specifically, that when the net force on an object is 0, it's either at rest or it's moving at a constant velocity. And when the net force is not equal to 0, it must be accelerating in some direction. Hope this was helpful, and I will see you very soon.